we're going to be looking at radioactive decay and in particular the exponential equations. Activity A is equal to the number of decays that occur per unit time. And activity also equals the decay constant multiplied by n, which is the number of undecayed nuclei present. Rearranging this equation and integrating gives you an exponential equation for n, where n is the number of undecayed nuclei remaining at time t, and n0 is the initial number of undecayed nuclei that was present. So I'm going to go through the proof of the exponential decay. It's not a proof you need to know for the exam. First, we multiply both sides of the equation with dt and divide both sides of the equation with n. And then we can integrate both sides of the equation. The right hand side we will integrate with respect to time t, or from the limits of 0 to time t. On the left hand side we'll integrate with respect to n, with the limits of n0, the initial number of nuclei at time equals 0, to limit n, the number of nuclei present at time t. We've also moved the minus sign to the other side of the equation. So integrating 1 divided by n with respect to n gives you the natural log of n with the limits n and n0. And integrating the right hand side of the equation with respect to time gives you minus lambda t. Substituting the limits gives us natural log of n minus the natural log of n0, which equals minus lambda t. And using the rules of log, natural log n minus natural log of n0 is equal to the natural log of n divided by n0. And then to remove the natural log, we will take an exponential. So n divided by n0 will equal the exponential of minus lambda t. And so you can see we get our exponential decay equation where n equals n0 e to the minus lambda t. So this equation is showing that radioactive decay is an exponential decay, and a feature of exponential decay is constant ratio property. So for equal increases in time, the same fraction of nuclei decays, which leads to the half-life concept. Half-life is the average time taken for half the radioactive nuclei to decay. So every half-life interval, half of the nuclei will decay. So the number of nuclei present follows an exponential decay, and because activity is directly proportional to the number of nuclei present, then activity follows an exponential decay. Now we're going to prove the half-life equation. So when the time equals the half-life, the number of nuclei present is half the initial value. So if we substitute these values in for t, t half, and n is n0 divided by 2. So the n0 cancels and it simplifies to a half equals e to the minus lambda t half. E to the minus lambda t half is equal to 1 divided by e to the power of lambda t half. If we cross multiply, then e to the power of lambda t half will equal 2. If we take natural logs on both sides, then the natural log of 2 will equal lambda multiplied by t half. And so rearranging, we can see our half-life is equal to the natural log of 2 divided by lambda, our decay constant. So the half-life is inversely proportional to the decay constant. The decay constant represents the fraction of nuclei that decays per unit time. So if we have a fast rate of decay, then that means a large fraction of the nuclei are decaying per unit time. So the decay constant has a large value, and so the half-life will have a small value.